NEC Article 450.3 states that Class 2 transformers are inherently protected against overloads and short circuits. Therefore, they do not require fusing on the secondary side. However, there are certain circumstances where fusing may be considered. Firstly, for protection against external faults. If the secondary side is connected to external wiring that is not inherently protected, such as conduit or cable, fusing can provide protection against short circuits and ground faults. Secondly, for noise reduction. Fusing can help reduce noise interference from actuators by providing a low impedance path for high-frequency currents. Based on the NEC code and the specific circumstances described, it is not necessary to fuse the secondary side of the transformers in the application. However, fusing may be considered if there is a risk of external faults or if noise reduction is a concern. Considering a 50 volt amps transformer, no fusing is required as the secondary side is not grounded. Considering a 96 volt amps transformer, if the secondary side is grounded to reduce noise, fusing with 3 fuses, one on each ungrounded conductor, may be considered. This provides protection against external faults and noise reduction. When determining whether or not to use a fuse and how many, it is important to consider several factors. These include the type of transformer, the application, and the relevant electrical codes. Firstly, the type of transformer must be taken into account. Class 2 transformers, as covered by NEC Article 450.3, are inherently protected against overloads and short circuits, so fusing is generally not required on the secondary side. However, other types of transformers may require fusing to protect against these conditions. Secondly, the application of the transformer is another key factor. If the transformer is used to power sensitive electronic equipment, fusing may be desirable to protect against voltage spikes or other electrical disturbances. Similarly, if the secondary side of the transformer is connected to external wiring that is not inherently protected, fusing may be necessary to protect against short circuits and ground faults. Thirdly, electrical codes must be considered. The NEC provides specific requirements for fusing transformers, and these requirements must be followed to ensure safe and code-compliant installations. For example, NEC Section 450.3 details protection requirements based on transformer size and application. In summary, fusing is not always required on the secondary side of transformers, especially for Class 2 transformers. However, fusing may be necessary in certain circumstances to protect against overloads, short circuits, ground faults, voltage spikes, and noise interference. When in doubt, consult with a qualified electrical engineer or inspector to ensure that the transformer is properly fused for the specific application and in compliance with all applicable electrical codes. To elaborate on the considerations for fusing, let's delve deeper into various aspects. Firstly, consider the transformer's volt-amps rating. Smaller transformers, such as the 50 volt amps and 96 volt amps units mentioned, often power control circuits or small devices. Larger transformers supply power to heavier loads, such as lighting, motors, or entire distribution panels. The size of the transformer directly impacts the potential fault current, influencing fuse selection. Secondly, the secondary voltage level must be considered. Common secondary voltages include 24 volts, 120 volts, 208 volts, 240 volts, 277 volts, and 480 volts. Lower voltages, such as 24 volts, are typically used for control circuits, while higher voltages power larger equipment. The voltage level affects the type of fuse required and its interrupting rating. Thirdly, the nature of the load is a critical aspect. Resistive loads, such as heating elements, draw a steady current. Inductive loads, such as motors, draw a high inrush current when starting. Capacitive loads, such as power supplies, can also exhibit high inrush currents. Fuse selection must accommodate these load characteristics to prevent nuisance tripping. Fourthly, the available fault current must be considered. A short circuit close to the transformer can result in a very high fault current. Fuses must have a sufficient interrupting rating to safely clear this fault current without rupturing or causing an arc flash. An electrical engineer typically performs a fault current study to determine the available fault current at various points in the electrical system. Fifthly, the type of overcurrent protection devices must be taken into account. Fuses are one type of overcurrent protection. Circuit breakers are another. Fuses offer fast response times and are typically less expensive than circuit breakers, but they require replacement after each overcurrent event. Circuit breakers can be reset after tripping, but they may have slower response times. Sixthly, selective coordination must be considered. Selective coordination ensures that only the overcurrent device closest to the fault trips, minimizing disruption to the rest of the electrical system. This requires careful selection and coordination of fuse and circuit breaker sizes and characteristics. Seventhly, ambient temperature must be considered. Fuse ratings are typically specified at a certain ambient temperature, such as 25 degrees Celsius or 77 degrees Fahrenheit. Higher ambient temperatures can derive fuse capacity, requiring larger fuse sizes. Eighthly, enclosure type must be taken into account. Fuses and circuit breakers must be installed in appropriate enclosures to protect against environmental factors such as moisture, dust, and corrosion. Enclosure selection depends on the location and application. Ninthly, the applicable electrical codes and standards must be considered. The NEC provides detailed requirements for overcurrent protection, including fuse sizing, interrupting ratings, and installation methods. UL standards provide testing and certification requirements for fuses and circuit breakers. Tenthly, the specific application requirements must be considered. Some applications may require special fuse characteristics, such as time delay fuses for motor starting or current limiting fuses for sensitive electronic equipment. The selection of fuses for 96 volt amps transformer used to power controlled devices, where one leg is grounded to reduce noise, requires careful consideration. Firstly, grounding one leg of the secondary creates a reference point, which can help reduce noise but also creates a potential path for ground faults. Secondly, the decision to use 3 fuses, one on each ungrounded conductor, offers the most comprehensive protection. This approach ensures that any overcurrent condition, whether a short circuit between conductors or a ground fault, will be quickly interrupted. Thirdly, the fuses must be sized appropriately for the transformer's secondary current rating. A 96 volt amps transformer with a 24 volt secondary will have a full load secondary current of 96 volt amps / 24 volts equals 4 amps. Fuses should be sized slightly above this value to avoid nuisance tripping during normal operation, but not so high that they fail to protect against overloads. A fuse rating of 5 amps or 6 amps may be appropriate. Fourthly, the type of fuse must be chosen to match the application. Fast-acting fuses provide quick response to overcurrents, but they are more prone to nuisance tripping. Time delay fuses can withstand temporary overloads, such as motor starting currents, without tripping. For a control circuit application, a time delay fuse may be preferable. Fifthly, the interrupting rating of the fuses must be sufficient to handle the available fault current. In most control circuit applications, the available fault current will be relatively low, but it is still important to select fuses with an adequate interrupting rating. A fuse with an interrupting rating of 10,000 amps or higher is generally recommended. Sixthly, proper installation practices are crucial. Fuses should be installed in appropriate fuse holders or blocks, and all connections should be tight and secure. The fuse holders should be properly labeled to indicate the fuse size and type. Seventhly, regular inspection and testing of the fuses and fuse holders are recommended to ensure that they are in good working condition. Fuses should be replaced immediately if they show any signs of damage or deterioration. In contrast, the 50 volt amps transformer, with no legs grounded, presents a different scenario. Firstly, since the secondary is not grounded, there is no direct path for ground faults. This reduces the risk of overcurrent conditions. Secondly, fusing the secondary side of the 50 volt amps transformer is generally not required by the NEC, as Class 2 transformers are inherently protected. Thirdly, however, fusing may still be considered for additional protection against short circuits or overloads. If fusing is desired, a single fuse in one of the secondary conductors may be sufficient. Fourthly, the fuse should be sized appropriately for the transformer's secondary current rating. A 50-volt amps transformer with a 24-volt secondary will have a full load secondary current of 50-volt amps/24 volts equals 2.8 amps. A fuse rating of 3 amps may be appropriate. Fifthly, the type of fuse and interrupting rating should be selected as described above. Sixthly, proper installation and maintenance practices should be followed. When discussing these considerations with an engineer, a clear and logical presentation is essential. Firstly, start by explaining the basic principles of overcurrent protection and the purpose of fuses. Secondly, then explain the NEC requirements for fusing transformers, including the exception for Class 2 transformers. Thirdly, present the specific details of the application, including the transformer sizes, secondary voltages, load characteristics, and grounding configuration. Fourthly, explain the rationale for your recommended fusing approach, including the benefits of using 3 fuses on the grounded 96-volt amps transformer and the potential for eliminating fusing on the ungrounded 50-volt amps transformer. Fifthly, provide supporting documentation such as NEC code sections, fuse data sheets, and fault current calculations. Sixthly, be prepared to answer questions and address any concerns that the engineer may have. Listen carefully to the engineer's perspective and be willing to compromise if necessary. Seventhly, emphasize the importance of safety and code compliance in all electrical installations. In summary, determining the appropriate fusing for Class 2 transformers requires a thorough understanding of electrical codes, transformer characteristics, load requirements, and safety considerations. The NEC provides guidance on transformer protection, but engineering judgment is often necessary to determine the best approach for a specific application. The decision of whether to use 1, 2, or 3 fuses on the secondary side of a transformer, particularly in control systems, depends on several factors, including grounding, fault current, and safety requirements. 1 fuse provides basic overcurrent protection. Firstly, it is the simplest and least expensive option. Secondly, it protects against short circuits and overloads in the secondary circuit. Thirdly, however, it does not provide protection against ground faults if the secondary is ungrounded. 2 fuses offer improved protection in some scenarios. Firstly, if the secondary is center-tapped and grounded, 2 fuses can protect against both overcurrents and ground faults. Secondly, 1 fuse is placed in each ungrounded conductor. Thirdly, this configuration ensures that both legs of the circuit are protected. 3 fuses provide the most comprehensive protection. Firstly, this configuration is typically used when the secondary is ungrounded and a high level of safety is required. Secondly, 1 fuse is placed in each conductor, including the neutral or grounded conductor if present. Thirdly, this protects against all types of faults, including short circuits, overloads, and ground faults. The choice between these options depends on the specific application and the level of protection required. In general, it is best to consult with a qualified electrical engineer to determine the most appropriate fusing strategy. The NEC provides specific requirements for transformer protection, and these requirements must be followed to ensure safe and code-compliant installations.